Good morning, everybody, and welcome to Tuesday, April 14th lesson on AP Chemistry. We're very excited to have you back today. Lots of great material for you about kinetics. Moving on to a new chapter, and we're really excited to share it with you. My name is Mr. Byrne. I'm coming at you from Glenbard West High School, just outside Chicago in Glen Ellen. Go Hilltoppers. Like I said, we're moving on to Unit 5 today, which is all about kinetics. Really nice, neat look at some equations, some connections back to your math classes, and some new ways of looking at equations from what we've looked at before. So like I said, I'm really excited to share this with you. Just a couple of quick reminders, like we want to tell you about at the beginning of every lesson. apstudents.org/exams2020 is your go-to for all sorts of information on all these topics that I listed over here on the right-hand side. If you have any questions, either check these out, send it to your teachers. You can log into this FAQ page and get lots of information about any questions that you have getting ready for our exams coming up. Hope you have a big smiley face target on Thursday, May 14th, 2020 for our testing date. Here in Chicago, we're going to be taking it at 1 o'clock, but based on your time around the world, you're going to be adjusted to a different time, but we're all going to be taking the test at exactly the same time. So we're excited to tackle that in just exactly a month from today, right? There you go. Very exciting. The format, just to remind you, you got 2 questions. You'll have 25 minutes to read and respond to the first one, 15 minutes to read and respond to the second one. And the focus really is going to be on your ability to explain phenomena, draw conclusions, analyze systems, support claims. So I hope that you've seen a lot of examples of how we're having you practice that over the past couple of weeks, and we'll continue to do so as we are planning more and more lessons for you. Okay, so let's get to our lesson overview. We'll start today, just like we start most days, with a warm-up and a review of yesterday's lessons from Mr. Fairbaugh. We'll go through the what you need to know and some practice, and then we'll finish up with some AP exam practice. Feel free at any point, like we remind you every day, you can stop this and review something that we said if we're going too fast. If I ask you to do a problem, then you should absolutely stop, try to do it, have a piece of paper, scratch paper. Today, you shouldn't need a periodic table, but never hurts to have one. If you have a copy of your equation sheet from AP Chemistry, that would be a great thing for you to have next to you too, because I'm going to point out a couple of things. And as you've probably noticed over the past couple of days of my lessons, I've been relying on this open source textbook, OpenStax. We have just a couple of images for today, but a couple of ideas that were really good in their text, and I want to share them with you as well. If you don't have your textbook at home, this is a great one to look at, but as usual, refer back to your textbook as a good resource for you, whenever you need it. Okay, so the topics we're going to look at are the first 3 topics in Unit 5 on kinetics, reaction rates, rate laws, and concentration changes over time. We'll be looking at integrated rate laws, how they differ from the rate law proper. And the skills we'll be looking at, you can see listed over here on the side: provide justifying or reasoning to justify a claim, relationships between variables. I feel like we've hit this one a lot lately. That was a great one. And then identifying theories, definitions, and mathematical relationships. So there's going to be a lot of connections between 5C and 5B today. So our warm-up is just a review of those problems from yesterday. If you have not had a chance to try these on your own, it's a great idea to stop at this point. Go back and look at yesterday's lesson. You can even, if you just want to look at the homework, zoom to the end and pick up those homework. I will project just the problem, so this would be a great opportunity maybe for you just to stop and take a look, try to answer the question on your own before you move on. So all of the questions, I think we have 4 of them today, have to do with a buffer solution. There's a great lesson yesterday from Mr. Fairbaugh on buffers. And this particular buffer contains hydrofluoric acid and sodium fluoride. So you remember that the best buffers are going to have a weak acid in them and a salt that contains the conjugate base of that weak acid. The Ka is given to us here of HF. The pKa, which would just be the negative log of this number, is equal to 3.17. So they gave us that number for us. And then the diagram is shown here as a particular representation of a buffer solution. Based on the information in the diagram, do you predict that the pH of the solution should be less than, equal to, or greater than 3.17, and justify your answer? So one of the key things that I heard from Mr. Faribault yesterday was this idea that we can analyze the concentrations of the acid and its conjugate. And that we know that if we have gotten to a position in if this may be a titration, this might be just analyzing a solution where the concentration of the acid is equal to the conjugate base, then the pH is equal to the pKa. So we're looking at a comparison between the two concentrations here. If we have more acid than conjugate base, we know that the pH is greater than the pKa. And if we have more conjugate base than acid, we know that the pH is greater than the pKa. I think maybe I said that the wrong way. We know, and go back here, if our acid is greater than our conjugate base, our pH is less than. And if our conjugate base is greater, then our pH is greater, okay? So what we would want to analyze over here is what is the ratio of hydrofluoric acid, excuse me, which is our weak acid, as related to our conjugate base. So we would count them up: 1, 2, 3, 4, 5, 6, 7, 8. We have 8 fluoride ions for only 4 HFs, 4 hydrofluoric acids. And so we can conclude that the fluoride ions are greater than the concentration of HF. And so therefore the pH of the solution should be greater than 3.17. Okay. Moving on to number 2, a buffer solution is made by mixing equal molar amounts of these things. And when a small amount of 12 molar nitric acid is added to the buffer, seem to remember a couple of problems like this from yesterday, the pH of the solution changes from 3.17 to 3.15. Write a balanced net ionic equation that accounts for the fact that the pH does not change significantly when the HNO3 is added to the buffer solution. And so our answer here talks about how we have a few fluoride ions that are floating around in solution, and the hydrogens are going to be eaten up by those fluorides to create HF. That this HF, because it is a weak acid, that means there's a strong bond between the hydrogen and the fluoride, and so they are hydrogen fluoride or hydrofluoric acid is going to stick together more than it's going to be separated, and when they're given the opportunity, they're going to bond to one another. So there is our balanced net ionic equation. So we know we have our ions here. Okay, the sodium would be a spectator ion here. The nitrate would be another spectator ion here. So you may have started this by looking at the complete ionic equation and then broke it down to the net ionic, but those spectator ions, they're just watching what's happening. They're not really involved in the reaction per se. Third question, determine the volume in milliliters of 10.0 molar NaOH that should be added to 1,000 milliliters of 1.0 molar HF to create a buffer solution that has a pH of 3.17. Justify with calculations. So the first thing we want to remember is that the desired pH is 3.17, so that's equal to the pKa of hydrofluoric acid. And so how do we get there? If we want the pH to be equal to the pKa, we need to prepare a solution in which our concentrations of HF and our concentrations of fluorides are equal to one another. So that goes back to a couple of things I said a couple of slides ago. We discussed that kind of pretty thoroughly yesterday. So half of the moles of HF must be converted to F minus. Okay, and then here's the equation. This is the neutralization equation that's going to tell us how we convert HFs into fluorides, right? So if our moles of HF, how did we get this? Let's look back up at our equation up here. We have 1 liter, 1,000 milliliters is 1 liter of 1 molar HF. So we have 1 mole of HF. So the moles of HF or NaOH that are needed would be half of that, right? So we want half of them to be used up. So HF is equal to 0.5 moles of NaOH. And how are we going to get that volume of 10 molar NaOH that's needed? We would take the moles times our the inverse of our molarity to get to the liters. Okay, and then if this is our liters, we're gonna convert that into milliliters because the question up here asked us to do it in milliliters. So 0.050 liters is equal to our 50 milliliters, and that would be our final answer for this one. Lastly, we have a buffer that has the following concentrations. A solution prepared with 500 milliliters above, with 500 milliliters of distilled water. Okay, so we're diluting that buffer. Do you predict the pH of the final solution to be less than, greater than, less than, equal to, or greater than? So we're seeing a pattern here of this common kind of question. So the dilution of the buffer with distilled water will decrease the concentration of each component, but the final concentrations will go to 0.5 and 0.5. Since they are still equal to one another, the addition of water decreases the concentration of both of them, right? We should maybe put the emphasis on this each. So because the concentrations, they have been diluted, the concentration was decreased, but they are still relative to one another, equal to each other. The pH of the final solution stays at 3.17. Okay. So there's our solutions to our homework from yesterday. We're going to move on from buffers into this conversation about kinetics and reaction rates, and how we could use a reaction rate and a rate law to describe what's happening in a chemical reaction. Okay. So if I were to give you just a very general equation like this, where I have some reactants, so two reactants react with one another in order to produce two X's and a P. Okay, this is very, very basic. Trying to keep the letters pretty simple for you. What we can say is that we could look at how the concentration of this reactant changes as a function of time. And we would call that the rate of decomposition. So how is this decomposing? How is this breaking down in order to make our products over here? And we'd say the rate of decomposition is negative because it's decomposing. We're losing reactants. Change in concentration of reactants over change in time, which we would simplify that way. And we could write with our deltas over here, delta R over delta T. So delta R concentration over delta T. And what's very common is for us to get data tables that share this data with us, right? That tell us what's happening as a function of time. So if you were to do we'll look at an equation you might have done in your class this year before you were dismissed, where you probably didn't have 24 hours to connect or to collect data, but maybe you did this in minutes, or this is probably too quickly to do seconds, but maybe your time was in seconds. You're going to look at how the concentration changed over time. You're going to calculate the delta R. So how much, what's the difference between these two? 0.5. What's the difference between these two? 0.25. You see how our changes over here. This is our change in concentration of R. What was our change in time? It's consistent, right? That's a good laboratory technique that we always had the same time difference. And then we calculated our rate of decomposition in moles per liter per hour for this one, right? And we can see that our rate here is, it's always negative, but the rate is actually getting smaller. And so if we graphed it, what we would see is we have initially the slope of this line right here. Okay, and your math teachers would be really excited if we talk about a rate and a slope as the same thing. Your physics teachers will also be excited if we talk about that way. You see that the slope of the line over here is much greater, and it's starting to gradually get closer to zero right here. So it's going to flatten out at some point, or theoretically flatten out. It would continue to go on until we had absolutely no reactants. We could write a reaction rate similarly for the rate of appearance of a product, right? So what you notice is missing here is our negative signs. So this would be positive numbers, right? I put some pluses over here. And what's interesting about this is that we can use stoichiometry to relate the rate of disappearance of R to the rate of appearance of P, right? And so these numbers probably look familiar to you, okay? But they are, because we're making, every time we use up two reactants, we're only making one product. These numbers are going to be smaller, even though they are similar. The math that we would do to calculate any of these things would be the same. Okay, so in class, you may have collected some kind of data like this, and then, or maybe you counted bubbles, or maybe we'll look at a couple of examples in a minute. But you would collect these two columns of data in class, and then you would have to calculate the everything over here from there. But my point here is talking about the fact that we have we could talk about the rate of disappearance or the rate of decomposition of a reactant and or the rate of appearance of a product. Both of them are going to be related to one another, and obviously connected. So here would be a graph of the rate of appearance of a product. Again, we have a pretty high positive slope here, but it's decreasing in its slope. So if we imagined a tangential line right here, that would give us the instantaneous slope. And as we move that along this line, it would be getting closer and closer to zero. And so then it's interesting if we put the two of them together. And this graph, R is our reactant that's decreasing, product is the P that's increasing, right? And then we could go so far as even add in that other product in there. The X product, the second product, the third species in this reaction. And what we see is that the rate of the reactant decomposing or disappearing and the rate of the products appearing are all stoichiometrically connected to one another, but they're not necessarily exactly the same, right? So if we had a sort of a complicated equation like this, okay, that we're told that the rate of disappearance of bromide ions at a particular moment during a reaction, okay, so this is instantaneous, right? I talked about if we're gonna look at this graph and say the instantaneous slope that's gonna change, we would wanna compare apples to apples, okay? So we're looking at the same time for all three of these situations. At a particular moment, the rate is 3.5 times 10 to the minus fourth moles per liter per second. Okay, so if that's for bromide, can you tell me what the rate of appearance for bromine is over here? Or what the rate of disappearance for hydrogen, or the rate of disappearance for BrO3, bromate? What I'd like to do is let's talk about your favorite. Have we done ice cream yet? I don't think we've done ice cream. So if your favorite ice cream is vanilla, let's go with, you do problem number one. If your favorite ice cream is chocolate, go ahead with problem number two. And if you have a different favorite kind of ice cream that's neither vanilla nor chocolate, why don't you go ahead and do problem number three. You can pause the video here, write out your solution, and I'll give you your answers in just a second. Okay, so what I would do in solving each of these is I would just multiply these numbers by the mole fractions of what from the equation. So we started out with the reaction, or with the rate that was given to us, okay? And we're gonna say that every time that 3 moles of bromine are produced, 5 moles of bromide are used up. So I can multiply by 3/5 to get to 2.1 times 10 to the minus fourth. The disappearance of hydrogen would be 6/5. So 6 moles of hydrogen for every 5 bromides. So we get an answer like this. And the disappearance of bromate is 1/5. So you may have been able to do some of these in your head, but I would imagine you'd need a calculator for some of them. Now let's think about what the signs on these should be. Right, so we have some inconsistency in terms of our signs. If this is the disappearance of bromide, we would probably talk about this as a negative number. I should have included a negative here. Okay, we're going to talk about the appearance of bromine. I would probably have a positive here, and these, because their disappearances, would also be negatives. So that's something that we would want to be a little bit more consistent on when we're looking at our answers. Okay. Now we know that, and this is probably another lab that you either have done or would have done in class with your students, with your teacher, where you would talk about what are some of the factors that are going to affect the rate of a equation or of a reaction. If we're talking about this one, how could we, if this is the rate at a given moment in time, what could we do in order to speed it up or slow it down? And we know that there are generally considered 4 different factors that we're going to look at that would affect whether the speed of a reaction, okay? And that would be the concentrations of the reactants, the temperature, the surface area, and catalysts. And without giving too much away for what we're going to talk about on Thursday, the bottom line is that it all comes down to collisions. And we talked about collisions a lot when we were talking about the gas laws. So I'd like you to go back and think about, kinetic molecular theory really only relates to gases in a closed container. So I'm not saying that this is the same as kinetic molecular theory, but the idea that collisions are a central idea in what's happening in chemical reactions is something that's very, very important. And we'll get into some more examples of that and some more explanation of that on Thursday. But what I'd like you to do just for today is to think, if any of these things are able to increase collisions, they will increase the rate of a reaction. If the molecules of the reactants can collide with one another more often or more strongly, then we are going to have a faster rate. And the inverse is also true. If you have fewer reactions or weaker reactions, fewer collisions or weaker collisions, then that's going to cause the rate of the reaction to go down. Okay, so let's look at these individually. So the reactant concentrations, if I increase the concentration, if I have a higher concentration, it would make sense that I would have a faster rate, correct? That means that I'm going to increase the likelihood of the collisions. There are probably going to be more collisions because the reactants are not as far away from each other as they were at lower concentrations. So how do I increase the concentration? Well, I could have something that is a more concentrated solution, less water if it's an aqueous solution. I could lower the volume if it's a gaseous reactants. Anything, I could add more of the solute to the constant volume of solution. Anything that's going to have the reactants closer to one another so that there will be more collisions will lead to a faster rate. We know that temperature is unique, and I'm going to encourage you to go back and look at our conversation earlier. I think it was last week where we talked a lot about the Maxwell-Boltzmann diagrams about what happens to the average speed of molecules as the temperature changes. But we know that temperature is proportional to kinetic energy. So at a higher temperature, you're going to have the molecules moving faster. Well, moving faster does two things. It either means that there's more collisions, or it means that those collisions are even stronger with one another, which we'll go into more specifically on Thursday. But either way, more collisions and stronger collisions is going to lead to faster rates. So an increase in temperature means an increase in the rate of the reaction. Surface area is a sort of a unique one for rates, something that we talk about. We don't talk about in many other places. But what you'll see typically here is whether you added a larger piece of the molecule of the substance to the beaker, or you crush it up, whether you dissolved it in water. I guess that's not a good one, but if you have like a one chunk versus two chunks of solution. So if we have a box of sodium per se that's in a block like this versus we cut it in half, well, now the surface area on those boxes in the middle is twice as big, right? So increasing surface area just increases the likelihood of collisions. I'll show you a diagram in just a second of that, because the reactants can connect with one another if there is more surface area. I like to talk in my class about if I did have that big chunk of sodium and the water was trying to react to it, the water can't travel all the way to the center part of those molecules. So in essence, those molecules are blocked by all of the molecules on the outside. And so we want to give collisions a possibility to happen by breaking up molecules into the largest amount of surface area, right? Which means the smallest pieces, the smallest particles. So greater surface area is going to lead to faster rates. And catalyst is kind of a unique situation. So I'm not going to say too much about that. I'm just going to encourage you to stay tuned for Thursday. It's important that we talk about catalysts in terms of their effect on a rate of a reaction. And these are the four big things that are going to affect the rates. But I don't want to get too much into the specifics of how a catalyst is going to react, except right now just to say it depends. And so let's put that off. Typically, catalysts are going to increase the rate of a reaction, but we'll look at all of the permutations of that on Thursday. Okay, so this would be a great slide here to take a screenshot of, either a mental screenshot or take some notes, just to remind yourselves of the four things that are the four factors that are going to affect the rate of a reaction and how they do so. In general, higher concentrations, higher temperatures, and greater surface area are going to lead to faster rates. All right. So let's look at a couple of different examples of comparing two different experiments to one another. So what I have here is calcium carbonate reacting with some acid to make calcium, water, and carbon dioxide. I want you to look at this reaction and think about the idea that the initial rates of formation of carbon dioxide gas from the chemical reaction are studied. So think back to some of the lab practices that we've looked at already this year, and think about, in these review lessons, and think about, how could I study the rate of formation of carbon dioxide gas? What would that look like in a lab? Just give you a second to ponder that. And I hope you came up with something that looks a little bit like this. Again, going back to our gas law conversation, where we were collecting a gas over water. Now, there's a couple different ways you could do that. This one, maybe because you have a piece of solid, it could look very much like that eudiometer example that I showed you when we were talking about the homework. You may just have something that looks like this, where you have a reaction producing gas, you have a glass tube that's going to run underneath some water, and as the gas is produced, it's going to displace some of the water. Now, if we wanted to be very specific, we may put a graduated cylinder here. We may put something like a eudiometer so we can measure the volume, but there's multiple different ways to do it. Just wanted to remind you, because this is a unique situation. How are we going to measure this rate of formation? Oh, well, we would probably do something like volume of gas produced. We also could do something with pressure. There's a couple different ways we can do it. Go back and look at your gas laws for further conversation of that. All right. So if we're looking at these two experiments, experiment number 1 and experiment number 2, the question is, which one, if any, will have the faster initial rate of formation of carbon dioxide gas? So which one might react faster, at least at the beginning? Would we see the bubbles of carbon dioxide gas being produced faster? And so what we're going to look through here, this is a very common theme today, is we're going to try to find what's the difference between experiment number 1 and experiment number 2. We have the same mass and they're in the same format of one of the reactants. We have the same volume of the other reactant. Here our concentrations are different, so that says to me, maybe that's going to be the key to what I'm looking at, but let's just make sure. Oh, yep, and our temperature stays the same. So what I'm seeing here is a larger initial concentration of acid at the same volume. Now, if the volume was different, this would obviously be a much more complicated problem. We're just doing this for review. So a larger concentration of the same volume means that my concentration went up. When I have a higher concentration of a reactant, what that means is that would give me a faster or a higher rate. And so the answer here is that experiment number 2 would have a faster initial rate, because there will be more collisions between the reactants when the concentration of acid is at a higher, when we have a higher concentration of the acid. Okay, here's experiment number 3 and experiment number 4. So we're going to do the same thing. Let's try to identify what is the thing that's different. You notice I changed our concentrations. They're back to being equal. Temperature is the same. Volume is the same. So now I have our mass of one reactant is a powder, and one of them is pellets. This is a word that we use a lot in chemistry. Where we talk about pellets would be much larger pieces. They may look like little stones, little rocks, maybe like BBs. Oops, I went backwards. Sorry about that. So that word pellets just means that they are relatively small pieces, but much bigger than a powder would be. And so the faster rate of the reaction would be the powder. And here's a diagram that might show you why. If these are the reactants on the inside here, and this is one of the reactants, so this would be the calcium carbonate maybe, and we have the acid on the outside that's trying to connect with the reactant. What you see here is these molecules on the inside can't react with the other reactant because they're blocked, right? Whereas if we break it up into little pieces, so this is the same number of particles on this side than we have on this side, now we have room on the inside here for both reactants to mix, and so the rate of the reaction would be much faster here, okay? So the answer to this one is, which one would be faster? The one that is in powder form, not the one that's in pellet form. Experiment 5 and number 6, what are we going to see here? Let's scan through our 2 experiments. What's different? And here we should identify that our temperature is different here. And so a higher temperature should give us a faster initial rate. Why is that? Because our particles will be moving around faster, which means they will have more collisions. And we'd probably want to point out also that they would have stronger collisions, both more and stronger collisions. And again, like I said, we're going to talk about that a lot on Thursday. So just getting these ideas kind of down in the back of your head is getting comfortable with these is a good idea. Okay, I'm going to move on to talking about some more mathematical representations. Okay, so we've spoken very much in general about particles and what's happening on a macroscopic level. So now let's look at the variables and try to relate these same ideas to a mathematical representation of what's happening in a rate. Okay, and so we have this idea of a rate law. So if I have given you an equation, again, I'm going to stick with it, just a general one for right now. X plus Y is equal to, or creates Z plus W. We'll look at some specifics in just a minute, but this is a general one. What we can do is write what we would call a rate law. And rate law has kind of 3 important parts to it. This is a very general rate law for this reaction up here. First thing I would like you to notice is that it includes the reactants only. Okay, we can talk about the rate, we can talk about what's happening in any kind of equation, calculate like we did earlier today for reactant or product. We can talk about the disappearance of reactants or the appearance of products if we wanted to, but by definition, if we're going to look at a rate law, we're only going to look at the reactants. Okay, so we have concentration of both of the reactants here. Okay, we're going to put exponents on those reactants that we'll talk about what we call the order. So in this example, M is the order with respect to X, N is the order with respect to Y, and then we could actually add M plus N together to say what's the overall order of the reaction. And that's going to be important as we get to the end of today's lesson, where we look at a number of ideas. And then the last important part of a rate law is that the fact that there is a rate constant. So this is going to define for us what how fast this rate goes. It's going to define help us understand what's happening. We want to remember that it's at a specific temperature. And we're going to spend some time today actually looking at units, where we are able to define the units on this K, and it would be specific based on what the order is. I know that sounds a little bit weird, and I'm going to walk you through a couple exercises on how we would derive the units here. But it's important to remember that unlike some of our other constants that we've looked at over the past couple of weeks, K in a rate law always has units, and it's really important that we get those units correct. So you're going to see questions where when we're defining the rate law, we need to know the value for K and what the units are on that K. So let's look at a specific example, okay? I'm sorry, no, I just want to double check with you if we could write, if we filled in M and N, I'm sorry, with some specific numbers, okay? If we looked at this first one, the order with respect to X is 1, the order with respect to Y is 1, so then the overall order is 2. We could have the rate with respect to X being a 2, the rate with respect to Y being a 1, and that gives us an overall order of 3. We switch the numbers to get an overall order of 3 as well. It's important to point out, guys, at this point that we could also have a 0 order. So you would have a 0 in here, which means that that reactant actually doesn't, the concentration of that reactant is not important in the overall rate law or the overall rate of the equation. We'll look at a couple of examples of that today, I think, or at least look at some of the math behind that, but we could include that in this chart if we wanted to, okay? So giving you some specific information about ozone here, we know that ozone reacts with nitric acid. what I'd like to do is to consider I'm going to give you a whole lot of data here, and we want to use that data to determine the rate law and the rate constant for the reaction at 25 degrees Celsius. So it's nice they tell it temperature's not changing, so we don't need to worry about the rate law changing or the rate constant changing. I'm sorry. Once we get to that rate constant, we will be good. The only way it would change is if it was at a different temperature. Okay, so when we're given a whole set of data here, this is a very typical data set for what you might see in a problem like this. Okay, and what we're looking for here, just like we did before, we have 4 trials along the left-hand side. And what we want to do is to identify places of difference between each of these trials. And even more so, we want to find places of difference and places of similarity. And we're going to compare those 2 different things. Okay, our goal here is to identify, first off, the exponents. What is the value of m? What is the value of n? Once we can identify them, then we're going to use our numbers. We're going to plug them in to solve for k, and then we'll plug in our units in order to solve for the units on k. So it's this sort of a 3, maybe even a 4-step process. If we say first we're going to solve for m, then we're going to solve for n. I'm actually going to do that in opposite. So I'm going to solve for n first, then m. The exponents you can do in either order, but we need to know our exponents before we can solve for k, and then we can get our units as well. Okay, so if we were to just analyze the first 2 trials, so I'm going to isolate the first 2 trials. And if this was me and I had this on a piece of paper in front of me, I might even take a second sheet of paper and just cover up trials number 3 and 4, just so they don't confuse me. Okay, because I want to be able to look at these trials and make some conclusions from them without getting distracted by the other ones. So we could make similar conclusions about any of the trials, but we're going to start with a simple example here. And what I notice between trial number 1 and trial number 2 is that the concentration of NO was not changed in those 2 experiments. Okay, so when the experimenter set up trial number 1 and set up trial number 2, they put the same concentration of NO into their reaction vessel. But the change that they did make was that they doubled the concentration of ozone. So 3.0 times 10 to the minus 6 is, we double it, we get to 6 times 10 to the minus 6. And so what we're going to ask ourselves is, what happened to the rate when we didn't change NO, we did change O3. And if you squint or you get your calculator out, you should be able to see that when the O3 doubled, so did the rate of the reaction. So this is, we're looking at the rate of production of NO2. Okay, and so what that tells us, and here's where another misconception, or we might make a little bit of a mistake, because the change is the same for both of these, this is defined as a first order, that the exponent here is 1. When this is doubled, this is also doubled. The same thing happened to both sets of data. And so because they're the same, we would put an exponent of 1 there. Now, I'll show you mathematically how we might prove that if the numbers are a little bit more difficult. But here, one confusion that somebody might make is, oh, I doubled this, and because it's a double, then I have to put a 2 up here. That's not the way we would analyze this. What I wanted to look at is, how did the rate change when I changed one of the reactant concentrations? And because this did the same thing as the reactant concentration, whether that was double, whether that was triple, quadruple, because these both say double, that tells us that our exponent up here is a 1. Okay, now let's look at trials number 3 and number 4. These are 2 good trials to look at because there's no change in the O3, the ozone concentration, but the concentration of NO doubled. And what we should notice over here is that the concentration of NO2 doubled as well. And because both doubled, right, we doubled the concentration here, this doubled, that's going to give us our order for NO of a 1 as well. Okay, so don't make the mistake of seeing the word double or thinking that means that you're going to have to put a 2 up there. All right. Now we need to solve for the value of k, and this is relatively straightforward. The math is a little bit wonky because you have scientific notation, but we're just going to plug in. We could actually do any of the 4 trials. So I'm going to start with number 1 as an example, and then encourage you to do 3, 4, 2, 3, or 4 to confirm. If it's a constant, it should be true at all situations, right? As long as the temperature does not change. So what I've done here is I've plugged in my rate on this side. I've plugged in my concentrations. I'm going to solve for k first, and then I should get to a value for k of 2.2 times 10 to the 7th. It's a very large number, which is fine. I should be comfortable with that. So I'm going to flash these up on the screen. I'm going to encourage you to stop the video and pick number 2, number 3, or number 4. Just pick one of those numbers, whatever your favorite number is, and confirm that you got 2.2 times 10 to the 7th. And then the last step here, which is where it gets a little bit tricky, is that we want to be able to determine the units. Okay, and I'm going to show you how I would be able to calculate them, and then I'll give you a chart which says basically what we can maybe just remember some of those, and you can decide what your style is to either memorize or to be able to derive these each time. So we've gotten to a point where our rate, we've identified this as our rate for this reaction under these circumstances, okay? And our units, which we came right off of our data table, okay? The rate is moles per liter per second, right? So molarity per second. The K that's in here is K just stays in there, but this concentration is moles per liter, okay? So should be able to say that K is moles per liter seconds. Just brought these down. I divided both sides and brought the moles per liter times moles per liter over to this side. And now I'm just going to cancel out. And so one of the moles cancels out with the other moles. One of the liters to the -1 cancels out with the other liters to the -1. And nothing else cancels out. So then I'm going to simplify into liters over moles times seconds. And typically in AP land, we would write those all with exponents. We'd say that that's equal to liters times moles to the -1st times seconds to the -1st, okay? So take a second and listen to that again. I'm running short on time here, so I'm gonna keep moving on, but if you wanna see my derivation of that again, or how I calculate that, please stop and rewind and go ahead and watch that again, okay? So our final answer here is that our rate is 2.2 times 10 to the 7th liters moles to the -1st, seconds to the -1st, times the concentration of NO times the concentration of O3. So there's our final answer, where we have the rate law and we have the rate constant with our units on it, okay? Let's walk through one more where the numbers are a little bit more complicated, okay? Here, I'm going to look at reactions number 1 and number 2, and I'm going to see that the first, when I doubled the reactant, I quadrupled the rate, okay? And so this is an example of where they are not the same. And so because our, the relationship here is the rate did twice as much as the change in the concentration, I'm going to put a exponent on our rate up there as a 2. Now you might get to the point where I would actually confirm the same thing would be right there. Like I said, it should, if this is the rate law, it should work in all circumstances. If your numbers are such as they are here, a little bit harder to see, you might want to have more of a mathematical way to break this down. So you certainly could take 2 different sets of data and plug them into your equation and then solve for X. The math here is a little bit trickier because we have to use some logs in order to isolate that X over there. But if we set, let's look and see which experiments did we use. I used trial 1 and trial 2, I believe. But again, you could use 2 and 3, 1 and 3. Any of them should work because this rate law is a law. I'm going to simplify both sides. The K cancels out. I haven't calculated K yet, but it cancels out in this circumstance because it's K over K, whatever it is, it's going to cancel out. I could take the log of both sides in order to isolate the X or bring the X down from the exponents. X is then equal to natural log of 2.5 times 10 to the -1 minus first, did I say 1th? Excuse me there, divided by the natural log of 5, e negative 1, and that is equal to 2 as well. And so that we're just confirming there what we sort of already knew. What I'm giving you here is just a methodology where you might want to be able to solve for x when the numbers don't jump off the page at you like they have in those other two equations, or those other two problems, okay? And there is, let's look at our units. Okay, so now we're going to solve both for k and for our units. Okay, so we've confirmed that it is a second order reaction. We're going to we can plug in any of our numbers. I've included our units here. And we come up with an answer that is 6.73, 10 to the minus 6th. And you notice that there's those units, while they're weird units, they are actually consistent with the one we had before. That other reaction was also an overall second order reaction and had the same units. And you'll see that if we can identify whether it's a zero, a first or second order, the units are going to be consistent across all of those. Okay, now so there's our final solution to that problem. Okay, looking on in this last couple of minutes that we have together, what happens if instead of looking at a rate law that compares the rate to the concentration, I want to look, because that's what is happening here, right? The rate law, which we know looks like that, relates the rate of a reaction to the concentration of the reactants, yes? Okay, so what we could do is we could integrate this, and your math teachers would be more than happy to talk to you about how to take the integral of any of the rate laws in order to relate the concentration of a reaction to time. And the whole purpose to this section and to the integrated rate laws is to relate concentration of a reaction to time. So we can do problems where you say, how much of this do you have after a certain amount of time, rather than what is the rate as a function of the concentration of this reactant. Okay, so if I gave you a reaction, A turns into B, and I told you that the rate law was K times the concentration of A to the first, I hope you recognize that as a first order rate law. Or yes, a first order rate law. That's a reaction is first order. Okay, and if I integrated it, again, talk to your pre-calc, your calculus teacher about how we would go from this initial reaction to the natural log of A is equal to negative KT plus the natural log of the initial concentration of A. All right, it's a pretty cool derivation of it, but we don't have time for that today. One of the many reasons why we would do this is because this looks very much like y is equal to mx plus b. I'm writing it in this line formation because we will look at some graphs. And if we were to put the natural log of a at a specific time, okay, on the y-axis, and we put time here on the x-axis, we should get a straight line. And even more so, for a first order reaction, we can see that the slope m here is equal to negative k. So this is super useful for being able to solve problems. And part of your homework today is to be able to look at what kind of a graph is forming a straight line. And if we take some data and we from an experiment and we manipulate it in several different ways, we make 3 different kinds of graphs, only one of them would be a straight line, and the one based on what's a straight line, we will know whether it's a zero order, a first order, or a second order. So let's be real clear. This is a first order reaction, and the straight line is created, the linear relationship is created only when we look at the natural log of A at time t as a function of time. If I were to look at C, just a different reaction, I'm just giving you a different one, different color, and I tell you that the exponent here is 2, you know that this is a second order reaction. So our integrated rate law is actually 1 over the concentration of C at time t is equal to negative KT plus 1/2 of the concentration of C. Again, and our Y is equal to MX plus B. And so our M is actually equal to K, and that should say positive K right there, right? Our M is equal to K. No, M is equal to negative K, I'm sorry. Yeah. Lastly, if we had a zero order, and this is the first time I've introduced a zero order in here for you. So zero order, we have our if this is a 0, we know that then the concentration of E is just 1. Anything to the 0 order is 1. So our rate is equal to K. This is our equation, and our M is equal to negative K. All right. On the equation, on the your AP chemistry equation sheet, you do have these equations are given to you. They're written in a little bit different format. They are written in the order of 0, first, and second order. So you would always have those with you. Here, this confirms that that should have been a positive K. I apologize for that. So our second order reaction would look like this. First order would look like this. And so this is our, these are the integrated rate laws for each of these kinds of reactions. If we are looking for the half-life, and this is a very specific circumstance where we're going to say that the concentration at time t is actually 1/2 of the initial concentration, right? So we could actually plug this in here, and then we could solve this equation for t, where we look at half-life. It turns out that for a first-order reaction, which is most radioactive decay, is going to have a half-life that's equal to 0.693 divided by K. And this equation is given, this part of this equation over here is given to you on your equation page as well. Okay, I'm going to run through this real quick, just recognizing that it's already 9:50 and you've been paying attention real well for a long time. We want to look at the value of K for radioactive decay of A. It's told to us that it's a first order reaction, and half-life is 8.5 minutes. So we just rearrange our equation to get our K. And then we plug that into our integrated rate law for first order to get how much time it would take. So this is an example of why we have this. We're solving for time. How long will it take for the concentration to drop from what we started to this final concentration? Okay, so there's just one quick example of how we might use each of those equations. I'm going to give you a sort of a different debrief today. This slide is, this chart is something that is very common in multiple different textbooks. I'm sure that you've seen it in different places. This is just a summary of all of the rate law information for 0, first, and second order reactions. I'm not a big fan of just memorizing things, right? But having kind of a snapshot of this in your brain to be able to refer back to, you will have your integrated rate laws written in the other format on the AP chemistry equation page, but this is this is a different way to look at it, and this gives you the y is equal to mx plus b format, which is going to help you to understand how what plot you need in order to get a linear fit for your data. Okay, and then here's a confirmation. Again, I'm sorry about the mix up on that slide over there, but the for a second order, K is equal to the slope, not the negative slope. All right, practice problems, and then you'll be on your way. Here's our first equation. What I'd like you to do is determine the rate law, the rate constant, and the orders with respect to each reactant, which you're going to need in order to get the rate law for this set of data right here. We're looking at laughing gas, so take a snapshot of that. And then your next one is right off of an AP test. So here's the data. I'm going to give you a second to take a snapshot of the data. And then there's multiple questions that are here. I really like this because it relates back to what we've talked about earlier with colorimetry. So here are basically 3 questions that we're looking at. Here's the data right next to question number 1. Here's the data next to question number 2. And here's the data next to question number 3. Okay, thank you so much for sticking with me. I know that was a hefty lesson today. Feel free to go back to apcentral.collegeboard.org anytime that you need, and look at our helpful resources down at the bottom link or at this tiny URL, and send your friends to cb.org/tech if you need to. Anybody that needs help, we want to make sure that they're showing us their extra work. Thanks so much for watching today, and have a great day. See ya.